All right, we had a little bit of a slow start, but I think we figured things out. So I partly promised you guys that we'll be having our first algorithm today, and I don't know if we're gonna quite make it there, but we'll make it there next lecture, I think. But we'll basically almost be there. We'll just need to take some derivatives at the end of the class that we won't finish probably. Okay, so that was the, I don't know, that was something. So where were we at? Where we were at was, I guess, trying to do supervised learning and trying to get a good learner. And we said that maybe a good idea is this like ERM, empirical risk minimization learner thing. And that roughly looked like you get an estimate of the expected loss, that's L hat, and then you need to, and we talked about how to do that last time. This is just your sample mean based on your data set. So I could even like write it here. This thing was like the sum I equal 1 to n of your loss function for the with the predictor taking in feature I, label I, and divided by the number of data points n. That's what that was. And now what was left was how are we going to optimize, how are we going to search over functions in our function class to minimize this object? And that's what we're going to talk about today. And the way this is going to look is the way that a lot of things have looked in this class, which is we're going to first talk and step back from machine learning and talk about how optimization works in general. If you just have like functions over some real values or multiple real values, these are like multivariate functions, and you may have done multivariate calculus where you took like derivatives of these things, tried to find their minimums, and we're going to somehow map that back to optimizing over function classes and solving this problem. That's going to be the story. And before we get into that, I just wanted to maybe mention one more thing about this whole problem setting and so on that will hopefully maybe like drive the point home about what we're doing here. So at the end of the day, right, we wanted to somehow produce a function that can predict labels well based on new features. And like really we wanted to say like, how do we pick which predictor does this better than others? And like we saw that you could like plot things and then maybe argue one's better than another or so on. And so let me frame the way what we've done in a different way. One nice way to choose between which predictor is better, which is what our learner is going to have to do, right, is if somehow we could just boil down the quality of a predictor to a single number, right? So if you take a predictor, plug it into something, and it gives you a number telling you the quality of that predictor, that would be amazing. Because if you'd had that, and that number signifies, let's say, smaller means better predictor, then you would just plug in all possible predictors into that function and pick the one that gives you the smallest number. And that's really what we did here. So the thing that hopefully I have motivated enough is that this expected loss is a quantity that you're like satisfied is a good way to describe the quality of your predictor with one number. And once you have that, then it's kind of like, then it's nice. You can then clearly distinguish which predictor is better than another, and then it's just left to search over those predictors. Okay, so hopefully that's another way to think about it. And of course, there's a lot of design decisions here, right? Like what loss do you pick? Different losses will cause you to have different values for different predictors. And those are all like, I don't know, like problem-specific things that you have to do and you have to choose. And some are better for some problems than others. And we roughly saw that for like regression problems, something like the squared or the absolute value loss makes sense. For classification ones, if you can't really measure the distance between your labels, it doesn't really make sense to take the distance, like the square distance between them, and so on. And there's all sorts of other theory and things that people do and so on that we won't get into details in this class, but like you can imagine, there's lots of research that people work on in that. Okay, so yeah, let's get into optimization now. How do we, once we have these numbers, right, and these are estimates of this number, then how do we find the function that makes this the smallest? Because there's a lot of functions here potentially, right? Like imagine you took all lines. How are you going to search over all possible lines that makes this number the smallest? That's what we're going to try to answer today. Okay, so we start with what is the beginning of optimization and what will be like a 4-lecture series on how to do this, because to be completely honest, this is kind of like maybe the biggest chunk of what research or like work goes into in machine learning, and what is really talked about is like how do you optimize these loss functions. And you'll hear things like, we're doing gradient descent or back propagation through our neural networks and stuff like this. And we'll get to all of that, but we're going to start like slower in simpler cases. And yeah, so this is a very big topic, I guess, in the field. Okay, I think I saw something in the chat. No, okay. Great. So as with the last lecture, I thought it'd be fun if I just write the notes on the spot, and we'll see how that goes. Hopefully that means we can actually still cover all the stuff I wanted to cover, but I think that's somehow more fun. Okay, so the topic is optimization, right? And this is like a whole field of mathematics on its own. Like, yeah, you can literally do your whole PhD, your career can be on just optimizing functions. This is a very, very rich topic. And we're just going to see like some of the, I don't know, main things that people use. So like roughly speaking, you can think of it as like optimization is just like this process of finding like the best solution from a set of options or a set of options, I guess. I got it. And then these things are vague, like what does solution mean? What do your options mean? Well, mathematically, it's going to be a little bit more clear. Second, like usually this means finding, or I'll just say this, it means usually minimizing, or of course, maximizing a function. So you like have your problem, you formulate it as like some input-output mapping, like, I don't know, you put in this much resources, you get this much money, and so on. And so you're trying to find like, and maybe there's like a constraint, like you don't have infinite resources, so you only have this much of each thing. And then you need to like find the most money you can get given your like resources and stuff like this. Means minimizing or maximizing some function. Okay. And as with probably most of the things in this class you've seen, things are going to be obvious at the beginning, but then hopefully that's good, because then it's going to be, we're going to get into something like, we're going to actually do this for more complicated functions, and the mapping should be very natural. Okay, and we're going to need to introduce some notation, as we have also done in this course. And so let's say we care about like, we want to find like the minimum of a function, right? So like, let's say you have a function. Okay, we have a function g. We're going to use g throughout here. And then when we get back to machine learning, we're going to use f. So like, just to not mix them up maybe. So you have g, let's say it comes from some domain w. And it maps you to numbers like, let's say real numbers or something like this. Okay. And so if you want the minimum of a function, you can like write it in words and so on. Another way to like write it is, well, let's do it like this. Let's suppose first, okay, let's work out some details so that it's like you can see everything. So imagine the function only mapped from like numbers 1, 2, and 3 to some real numbers. Well, then like the usual math notation that people use to write the minimum of a set of objects is you write the word minimum, and then you write the set of objects. And the set of objects you're going to care about is like all the values of the function that it can output. So you'd write like g with 1 as input, 2 as input, and 3 as input. Okay, and this value would be the minimum of your function, clearly, right? But you can already see that like if you have a lot of inputs to your function, this notation gets a little bit ugly. And then you would have to write things like, oh, if this was like, let's say from the set W, then you'd have to like write, okay, well, now I need to write the set of all values my function can take. And we can do that. This would be like g of little w, perhaps, such that w is an element of w. And that's still okay. But people usually don't do this. And so the equivalent to this notation that people use, and we're going to use, and you're going to see a lot in probably the rest of your life for machine learning, is you will write your function g, you plug in like some value w, and you want the minimum of it. And then under the minimum, you write the domain for which you're looking for the minimum, and you plug in. And so that would be like, this little w comes from capital W. So this is like the equivalent meaning of that. Okay, and we're going to use this a lot. So this is the minimum of their function. And yeah, so you know what that is. And then the other thing we're also going to care about right? So this is the minimum value of your function. You might also care about at what value of w does that minimum value get achieved at? And this is called what is the minimizer, right? So what value of w makes this the smallest? And the way we write that is we write the argument to the function that makes this the smallest. So we write argmin. Okay. This is kind of the extent of the notation you're going to need to know. So that's the w that achieves the minimum here. Okay. And if we give this a name, usually this will be called like something like w star. It's the point at which the function is maximized. Well, then you get the property that the argmin, this w star, satisfies that min, or maybe I can write it like this. So on the left here, this minimum value is obviously equal to g at the minimizer. And so this is like the definition of the argmin. It's the value at which, if you plug in here, you achieve the minimum value of your function. Okay, this is the extent of the notation you're going to need because we're going to keep using it a lot. We're going to care about the minimizers and the minimum values. And okay, we'll talk about that there's a relationship between minimums and maximums in a moment. But before that, let's just do a quick little example of something you probably have seen many times in calculus before. And that is like, let's take a specific function, and let's say it's the quadratic function, parabola, w squared. And let's just do the minimization visually first. And we're going to kind of use this as an example throughout to give us intuition as to how the visual can then be translated to math, which you already know about probably, but we're just going to review. Okay, it doesn't seem to want to give me a nice curve, but so this is w squared. And like visually, I can clearly minimize this function. Okay, and I should say that, so this is g of w, and let's say g was a function from the real numbers to the real numbers. So its domain was actually all the reals. So you wanted the minimum over all possible real numbers of this function. And like visually, you can see what is the minimum? Well, clearly it's over here. And what is the minimizer? Clearly it's 0, right? And so, yeah, let's just, so that's what we get. So visually, like we have the w, our domain is the real numbers, right? And then just to like drive the point home, the things we just saw above, it would say that the minimum value of this function g of w, where w comes from the domain R, all real numbers, well, that will be 0. And we just saw that like visually. We're going to work this out in a second. And the argmin, which is the w that achieves this minimum, is, I guess, somewhat confusingly also the exact same thing, which is also 0, and this would be w star. But you get the property that we talked about before, which is that the minimum value is the same as the function with the minimizer w star plugged in, right? Because g of 0, you can see is just 0. Okay, so super simple. But now let's just, get a feel for something that can be a little bit interesting, which is, I said that the domain seems to be somewhat important in these things because I said you want to take the minimum over like the domain here. And so what happens if I change the domain? So for instance, what if I said that, okay, maybe I should have wrote this more generally. So g would be a function from this calligraphic w. And what if I now said, oh, w is actually no longer the real numbers, but instead it's, it only has a domain of 2 numbers, like -1 and 2. Those are the only 2 places you care about. You want to find the minimum value of the function at 2 points. Well, now clearly this is going to be different, right? It's like -1's over here, 2's over here. This has a value, from plugging into the function. It has a value of 1. Over here, you have a value of 4. And so now clearly the minimum is going to be different. So, yeah. So the minimum of w over this new set, -1 and 2, of g of w now becomes 1. And the argmin, and so now we actually get a different argmin. The w that the minimizer of this function, the argmin, is equal to -1, right? This tells you the point on the x-axis. This is the w's that achieves this. Okay, and so once again, if we look, this guy up here, this 1, is equal to g of w star, right? Which is like -1 squared. Okay, so super simple, but this kind of shows a bunch of important things that we can just think about visually just a little bit more maybe, which is like, notice in this case, kind of like when the domain was all of the values and they were like continuous, you can kind of like, smoothly see that you can look at the function, you can like smoothly kind of go down and find its minimum, and the function's defined at all of these points, and that will be very nice. I'm just kind of, I don't know, building some intuition for a little bit later. And when things are discrete, you have like a discrete domain, really what you have to do to like look for a minimizer is you kind of have to test your function at every single point. So you'd have to be like, oh, what is the value here? What is the value here? And then you have to compare them all. And that's going to be another story about how you do things when things are discrete, but these will be different. And in general, you can imagine when your function's more like higher dimensional and stuff, just visually looking for the minimum is not going to work so well anymore. Okay. And so before talking about how we tackle this in the more general sense, which you probably learned in calculus already, but we'll review it. We're just going to talk about this, like why we're only talking about minimizing. So people in optimization world always just talk about minimizing things. And the reason we only talk about that is because you can always maximize the function if you've already minimized it. Okay, so there's a relationship between maximizing and minimizing. Okay. I'm not going to write things in English to save time. So this is the relationship, right? Let's just draw it visually. And then we do the math again. And maybe I'll just do this with one plot. So suppose you now have like this quadratic function, right? And so this is g of w. And we had these points, which was like the minimum value was over here, right? This was the minimum value. And the minimizer was this point here, which was the value of w. So this we gave w star, and this value over here was a g of w star. Okay. Well, the relationship between these two things is that if you take this function and you take its negative, then you're going to get the following looking function. Okay. And the story is going to be that the maximum of the negative of the function, right? This is negative g of w. So the maximum of the negative of the function is not going to be the same as the minimum, but the minimizers will stay the same. And the way you get the minimum or the maximum back is if you just take this value and take a negative of it again. This is going to be like the rough idea, which we're going to show in math in a second. So notice that this is now negative g of w star, which can in general be different than g of w star. And you can see, how do you get it back? Well, you take the negative again, obviously, right? So that's going to be what you want to do. So like, in some sense, this is this, right? But notice that the minimizer is the same of both. Okay. So the story is like, if you've minimized the function, then if you needed like the maximum of some other function, well, then you just minimize the negative of the function, is the story. And the relationship, like more precisely, is the following, which is the argmin, we call the argmin like w star, of g of w is equal to the argmax of negative g of w. And this always holds true. And if you want the corresponding minimum value, which is not the, like this is the minimizer, if you want the actual minimum value, well, we've seen that like g of w star will give you the minimum. Right? And we also saw that, let's see how I would write this. Yeah, we also saw, well, the claim is going to be the following. We also saw that, like, if you took the maximum of negative g of w, then you get like a point like this. And if you then apply the negative outside, this is what our intuition was saying, then you should get g of w star back. And this is like, you get the following, which is this is the negative of g of w star. And yeah, and the reason we know that is because the maximum of this, right, is achieved by the argmax of this, which is w star. So now I've just plugged in w star into this expression. So we know these things are equal. And then you get the corresponding result. Okay, so these are some relationships. So basically, if you minimize something, you can always solve the equivalent maximization problem by just, like, if someone says maximize g of w, well, you'll be like, okay, I'm just going to minimize negative g of w for you, and then give you your final answer as the negative value of what I got. And hopefully that clarifies. Yeah. That's right. That's why the minimum of g of w is equal to the negative of the maximum of negative g of w, right? So let's look here. This is negative g of w. This is the maximum of negative g of w. And then if we take another negative outside, this will take this point and flip it here. And once again, the way this works is the maximum of g of w is achieved, right, at w star. As we saw, it's achieved at the same point. So what I can do is, instead of this term, I can just plug in, like, I take this function and I plug in the value at which it's maximized, which is w star. So you get this. That's this inner term. And then you can see mathematically these are indeed the same. I mean, maybe I should have wrote it like the other way around. This is kind of ugly. So, like, we know this. This is definitely a lot nicer. And we know this, clearly. This is just like simple math. And then you can do this, right? Okay. So hopefully that clarifies. Like, if you have g of w, it's clearly equal to the negative of negative g of w. We know this, and we know that negative g of w, this thing, is exactly equal to the maximizer of this. Okay, so that's enough, like, preamble to build up to actually getting into solving these problems. And so the question is, like, how to solve minimization problems. And that is, okay, so far, hopefully I've motivated that minimization problems are sufficient to talk about. And that's all we're going to need to talk about. And then we can always maximize things. And now we're going to just basically spend the rest of this class and 3 more classes about how to do this. And we're only going to cover a very, like, I guess, small part of this stuff to some extent. But so first, let me just point out there's kind of like 2 cases, as we have already seen. And it goes kind of as follows, which is, you saw that if the domain W is discrete, right, then kind of, well, like, if there's no extra structure and stuff like this, really all you have to do, or all you can do, is compare literally the value of the function at every possible input point, every value in the domain, and then find the minimum. And that turns out to be quite inefficient, and this is called, like, discrete optimization, and it's like a very complicated topic in general, and there's no really great ways to optimize these discrete functions. So if, like, W is discrete, then we compare G of W for all the points, for all Ws. And that's kind of the extent of what you need to know for minimization if you have a discrete domain. You just plug in every single element into the domain, compare them, and pick the minimum. And we're not going to get any more into this discrete setting because it's kind of hard. So what do? Well, we have, like, a lot of power in kind of how we set up our problems. And you already saw that we picked features that were part of, like, RD, so things were continuous and so on. And the reason why is because then we can use a lot of the tools in calculus. And there, we're going to be able to make use of derivatives. And so, like, roughly speaking, if W is continuous, then we can sometimes if the function is nice enough, we can sometimes use derivatives to help us. And we're going to, for this course and in machine learning, we're going to choose the loss function and our predictor class, like the predictors in our function class, to make it such that things are nice and so that we can use derivatives. And so now we're going to study like what are the properties of when we can use derivatives and get like easily optimized functions. Okay, so we're going to focus on this case. This is going to be like our point of study. And in particular, we're going to make some assumptions on this function g of w that's going to help. And the assumptions we're going to make is like, I guess the following. Oh, like first of all, we're going to just always assume this is continuous, I guess. So we, in the second case, and we're also going to assume some, okay, maybe let's kind of like deduce what the next two assumptions are going to be, sort of. So if we go back to this function, like what allowed us to find the minimum, like kind of super easily to some extent. And it's something like, well, you know, one thing is that this function was not like this, let's say. And in higher dimensions, it would be even more complicated. And so it's just clear, like there's, like if you found a point at which it like has this like bowl shape, some people call it like a convex shape, well, then you knew that that point, this would be called like your local minimum, is the global minimum. And so if you have functions like this, you could encounter many points that are minimums, and then you'd have to somehow compare them and maybe find them all and stuff like this. So we're going to not want functions like this. These are called the non-convex functions. So we're going to want functions that are bowl-shaped, which are called convex. And this is a very like, okay, so that's going to be a very, very important name, assumption, and everything. And there's various ways to define convexity. And we're just going to opt for the like simplest one, which you probably heard in calculus, which needs one more assumption. And the way you can define convexity is that if you first look at the rate of change, which is like the derivatives, right? You can look at the derivative like at this point, and then the rate of change at this point, and this. You'll see that for these convex functions, the slope, as you move along the x-axis, the w-axis here, that slope is always increasing. And so the rate of change of the rate of change is called the second derivative. And as long as that's non-negative, then that means that your slope, right, keeps becoming more and more positive, or like keeps increasing, right? Which is the first derivative keeps increasing. Okay, so these are going to be the two properties we want, which is that it's convex and twice differentiable. Okay, so g of w, or I guess v, is convex and twice differentiable. And when it won't be twice differentiable is if you have like sharp jumps in your function. And so like the absolute value will cause kind of problems for this. And there you have to, there's ways to deal with it. You can see that the absolute value is still convex, which we saw before, but it's not twice differentiable. And so we're not going to deal with it for these reasons because the math is a little uglier. But there you use things called subgradients. And I guess you see it if you take 467. That's like the follow-up course. They deal with this stuff more. Okay, but for this course, we're just doing all the simple things, which hopefully, like, I don't know, whets your appetite for what can be done in other things. Okay. Oh, another thing to say is like, so there's literally like massive fields on what is called convex optimization. And the rough story, and this has kind of been like the discovery of the past maybe like 30, 40 years ago, and like it's very hot now, which is people have kind of discovered if you have a function that's convex, then you're basically done. And it's like, it's almost a joke, like to the extent of like, if you're working on some like problem and you're like struggling, whatever, and as soon as you show that the function is convex, you might as well, you can put everything down, you're done. Your project is finished, there's nothing left to do. And until then, you have no idea if you're gonna be able to solve things efficiently. So like that's how kind of how efficient these like convex solvers are. And to like, what I mean by that is you can literally like in code just, if you have a convex function, you can just use different libraries and they will solve your thing like immediately. You don't have to deal with any of these details for the most part. And that's how it works in machine learning too. There's all these optimization libraries and things like this. But we're gonna like work out some things by hand with doing derivatives and so on, just to get a feel for how it works. And then that's going to also drive, obviously, then you're going to need to make good choices on your loss function and your predictor classes to achieve these type of things. Okay. So shall we get into how this works? Yeah. So maybe let's define some of these terms. So first of all, I mean, twice differentiable is quite simple, as you saw. So twice differentiable just means that G, and we write like G double prime for its second derivative, exists for all W in the domain. That's going to be assumption. You can take the second derivative and it actually exists. If you have like sharp jumps like this, then you won't have derivatives at this point, and that's what it means to exist. But yeah, that's, I think most things should be twice differential. And the other thing is, what does convexity mean? And we've already seen this, which is convexity means you kind of have this like bowl-shaped thing. And most of the time, if you plot your function like 1D and you get a bowl-shaped thing, you're kind of good to go. But formally, it's that the second derivative is greater than or equal to 0 for all W. Okay, so these are going to be the two assumptions. You're going to need to test this occasionally for some problems. And the intuition should be that G of W, your function, if you look at it, it looks like a bowl. In one dimension or in two dimensions, or if you have a higher dimensional one, you can like take its slices and stuff like this. And yeah, and so the function we saw earlier is convex, and if you see the course notes, it like takes some derivatives and sees, okay, let's just quickly do it. So like in the example above, if we just work out some of the details, we had like G of W, well, it equals to W squared, and we can take its derivative. So let's just do that. G prime of W equals to 2W, G double prime of W equals to 2, and that's greater than 0. It's convex, and since we could take its second derivative, it's twice differentiable, so we had a convex function. Great. And you can do that for all sorts of other functions and so on. Okay. And now how do we find the minimum? Okay. And finding the minimum is going to have like two cases. And it's going to, once again, depend on the domain. And you've probably seen this in calculus, which is like, you know, if you have like a bounded domain, you have to check the kind of the edges to see if one of those achieves the minimum or maximum. And like, yeah, I mean, visually, like, what is it? Like, if I just draw this thing, right? We said that this was the minimum if you consider all real numbers. But if you only, let's say, consider numbers like here till here, so this would be like this region, well, then clearly your minimum is different. Your minimum would be like over here. That's going to be the rough story. So if you have like this like bounded domain, it's not just all real numbers, you're going to need to check the sides as well. Okay, so there's like two cases. Like the first case is one. So in this, and so far we're only dealing with, we're going to deal with the one-dimensional case for continuous things, and then we'll move on to higher dimensions. So if W is equal to the real numbers, then W star is the solution to G prime of W, and then you set it to 0. So the derivative set to 0. We've seen this before. And yeah, let's do it above in this example. So G prime of W equals to 2W, set it to 0. Let's solve. That tells me that W equals 0. That's the minimum. However, what happens if W equals 0 is not in your domain? You could still get this like answer, but you'll be like, oh wait, I'm not allowed to consider that. If I only defined my function to be in some subset of the real numbers, then I need to actually check if it's if the solution to this thing is in the domain, and if it's not, then I should check both ends of it and see if things are okay. Yeah, and once again, we've assumed things are convex, right? So there's no local minimums living somewhere else and things like this. So if instead this is an interval, and of course you could have like unions of intervals and so on, but we won't encounter that. Well then, W star is still the solution, of this thing if W star, or like, okay, if it is in W. Wow, there's 4 two-letter words in a row. That's crazy. Okay, anyways, yeah, so if you have this, if the solution is inside W, then you're fine, like as we had seen above. So if like A to B, this is A, this is B. If A was like further out, like over here, then of course it captures this and you're allowed to use that. And otherwise, W star is A or B. And so you check both of them and then pick the smaller one. And so like for the case above, if we instead restricted, let's say, W to be equal, so this was the case, maybe I should make this one in purple. This was the case where like W was the real number, so we were all good. Or alternatively, another option is I could have made it like, let's say, -1 to 1. We were still fine because the minimum was within it. But if instead I made the domain 1 to 2, maybe that's what this looks like over here, well, then you would check and see, oh, W star 0 is not in here. So now I have to check the edges, or the endpoints of the function. So I check g of 1, that's equal to 1. I check g of 2, that's equal to 4. And I'm like, oh, then clearly this implies that W star here is equal to 1. Because at the point 1, I get the value of 1, which is smaller than the other endpoint 4. And this is because we have convexity, so we know that it must be that you go from this endpoint, you're increasing all the time, or if it was like in this region, you were decreasing all the time. That's why it's okay to check the endpoints. Okay, so hopefully that has explained some of these things. And then like maybe in one other example before we get into some more fun is what happens when things are not like convex. Well, let's say I give you a function like W cubed, right? So you could go ahead and you could be like, oh, okay, let's take its derivative and set it to 0. And so let's do these calculations. You get 3W squared. You get the second derivative of W is equal to 6W. And then you're like, okay, second derivative exists. Let's forget about checking for convexity in a second. And then you're like, okay, I'm going to go and do like, check my G prime of W, 3W squared equals to 0. And then I'm going to get, oh, the minimizer is W star equal to 0. And then I go and plot my function. And I quickly find out that there is a problem because I just found that my minimizer is here. And if W was the real numbers, then the minimizer is like, I mean, it's negative infinity. You can get it as small as you want. And what went wrong here? Well, obviously, it's the fact that we needed to check like if this is true. And of course, it's not true. So it's not greater than or equal to 0. Like, for instance, if W equals -1. Okay. This is where convexity goes wrong, and you have problems, and so on. Okay. And yeah, and the other case you kind of can encounter, as we saw before, is your function could look like this, where it has like multiple minimums. And then if you solve for the point where it's equal to 0, you can get a bunch of minimums, and then you'd have to pick like the smallest one, and so on. But we're not going to deal with that because of we're going to get into slightly more complicated things, and then this is not going to work great. Okay, so, and this is clearly just like visually, if someone were to give you a function like this, you should be able to visually say that, oh, this is clearly not convex. Just because of this intuition that you have that it has to be bowl-shaped. And if you have this like, so here you would have that the second derivative is greater than 0, but then as soon as you get to here, you get that the second derivative is less than 0 because your slopes start decreasing. They get more and more negative, right? And then it's positive again and negative. And anyways, you'll, I guess, work out some of the stuff in your assignment. Okay, so this is probably all calculus, like first year calculus stuff. Now we move on to what is kind of like, I guess, second year maybe calculus. So we're going to do multidimensional minimization. And of course, this is going to be important for machine learning stuff because you can see that like, you know, like our features are very high, like they can be high dimensional, like R to the D could be large and so on. So we're going to somehow need to know how to minimize over multiple dimensions. And yeah, so the multi-dimensional case we consider is when this domain is equal to RD. So once again, we're going to still consider these continuous domains, and we're going to make use of derivatives and stuff. And this is for the case where D is greater than 1. And in the cases above, D was equal to 1. Or it had some like small interval. Okay, and we're going to consider this, and we're going to just assume from now on that it's just always convex. And okay. And in multiple dimensions, convexity like is going to look like you just have like a 2-dimensional bowl or a 3-dimensional bowl, which you can't really visualize the 3-dimensional one. And there's ways to check for this mathematically. And it stems from the same idea as checking that the second derivative is greater than 0. But you might remember in like multiple dimensions, you can take derivatives in each dimension, right? So if you have like d dimensions, then there's d partial derivatives. And then if you want to take a second derivative, since every one of those partial derivatives is itself a function of RD, potentially, you then need to take d more derivatives of every one of those d things. So then you get a matrix of derivatives. That thing is called a Hessian. You're not going to need to know this. But what's going to happen after that is you're going to have to somehow check if this Hessian, this matrix, is somehow greater than 0. And the equivalence of this in like matrix world of a function, or like a number being greater than 0 for matrices of a matrix being greater than 0, people will write things like, okay, just for fun. So if people write like a matrix A is curly, like okay, they do this like curly thing, greater than 0, and this is like a generalized inequality. And what it means is your matrix is positive definite or positive semi-definite, meaning that if you take any number and you multiply by it from both sides, you're always going to get a number that's greater than 0. And this turns out to be like the generalization that somehow is the right generalization of checking that a number or like a derivative is greater than 0. And this, if you check this, you get that things are indeed convex. And since, once again, like at the end of the day, this is just more mathematical steps, you kind of get the idea. You're trying to check these second derivatives are greater than 0. We're not going to work this out. Once again, in 467, you do compute 467. But hopefully, just from seeing the 1D case, you get the intuition, and you can just imagine that all you're trying to do is check that it's bowl-shaped, which means you're trying to check that the rate of change in every dimension is indeed positive. Okay, so the note that I wanted to make is this is like more complicated, and if D is greater than 1, I will always tell you that it's convex. I will always tell you if it's convex. Okay, so what you should have gotten up to now is the fact that if you wanted to minimize functions, the domain being continuous and your function being convex is very nice because the process becomes as simple as like taking a derivative and setting it to 0. And you can get that if you do your checks and make sure things are indeed convex, and you can do that check and so on. Okay, and so now the story is going to be very similar in multiple dimensions. So in multiple dimensions, we now have like a function g, but now that g has a domain that's d-dimensional. So I'm going to write that it takes in a vector w. And I want to find the minimum value of the function, okay, when you search over all vectors in RD. And since we're going to care about minimizers, we're going to look for the argmin, or the argument that minimizes this vector valued function, where W, this W vector, comes from RD, which is the domain. Okay. Right. And like this will be RD. And this now gives you what we will call W star vector, which, to be very explicit, is actually going to be D values, right? Is going to be like W star 1 up to W star D transpose. Okay, so this is a column. Well, this is a row vector because I've transposed it. And yeah, hopefully that will make sense. That's kind of like, it tells you the minimizer in each dimension. I think it actually is going to be useful to show you a picture. So let me just pull up a picture that I think I have, and I will copy and paste it here of a three-dimensional looking thing. Excellent. Okay. So now we've got our, so here RD is 2, like V is 2. And now instead of having like a parabola, oh no, okay. The only way I know how to fix this is to close Notability and reopen it. Okay, back to business. So instead of just having like a 1D parabola, we now have this 2D bowl-shaped thing. And how are we going to find the minimizer? Well, you can see that like the minimizer is going to be at a point, well, at a point in 2D space, and that point will be described by two numbers, W star 1 and W star 2. And that's our vector. That's this thing. Okay. And you can see that, unsurprisingly, the way to do this is going to be very similar, right? It's like, okay, if I want to find W star 1, what do I do? Well, I kind of have a parabola in that dimension. So probably if I just take its first derivative and set it to 0, I'm going to get the W1 point. And if I take the derivative and set it to 0 in the second one, I'm going to get W2. And this turns out to be right for things when they're convex. Okay. And so to calculate this, guy, yeah, we calculate W star vector by solving. Now we have to write the partial derivative, and for partial derivatives, you don't write GW vector prime. There's no meaning of this. And so then so before like when we didn't have vectors, you could have wrote G prime. Okay, let me just be very clear what happened. You could have also wrote this, which is you take the derivative of G with respect to W, and that's a function of W. These were equivalent notations from before. People like to use this in one dimensions, but it's the same as this. But when you get to multiple dimensions, we no longer use this notation. And instead we use this, but people like to write that it's now a partial derivative, so they write this del thing like this. Okay. And now you actually will take now this thing will become a function in general of W vector, but you take the partial derivative of a particular index, I. Okay, and so we need to solve this first partial derivative equal to 0 equation for all the dimensions, for all I. Okay, and I guess I use J, so let me just keep. For all J that are an element of the set 1 up to D. So that should make complete sense. Hopefully, you take the partial derivative in every dimension, set it to 0, and you get the corresponding W star for that index. You put it together into one vector, and you get W star vector. That gives you this point here. Okay, and this function over here, let's just do it for the function on the right. This function on the right, you should not be surprised, is like the kind of quadratic or parabola extension to higher dimensions, or for 2 dimensions. And the way you do that for higher dimensions is you write GW vector. Well, here the W vector is going to be 2-dimensional, so it's just going to be like W1, W2. So W is R2. And the function is just W1 squared plus W2 squared. And you can do this for more dimensions, and you get these like equivalent bowl-shaped things in higher dimensions that we can't visualize. Okay, and then let's solve this. Quite easy to do. Hopefully don't get confused. This is not the number 2, it is the del operator for partial derivatives. So let's do it for W1, the partial derivative of G. And if we do that calculation, what do we get? We get that it's 2 times W1. And we set that then to 0. And that implies that W1 star should be equal to 0, which, as you see, is exactly what this picture shows you. And it's the same story for W2. So then you get W2 star equal to 0 as well. And you get your solution, and you're like, okay, my W star vector is equal to 0, comma 0 transpose, which is exactly this point over here. Okay, and you can imagine, and you're going to do this in your assignments, if you now have functions that are more complicated. So for instance, if you have like, I don't know, W1 squared, W2 squared, now when you take derivatives, you still don't, you don't end up with just a function of W1, you end up with a function of W1 times W2. Actually, you know what, let's do this, because this will be very important, and I didn't do this last year, and I feel like it, then when you get to the machine learning thing, it gets confusing because you do have these multiplicative relationships. So let's just do one more quick example. So suppose that G of W1 W2 is equal to W1 squared W2 squared. Okay, and I'm going to hopefully highlight something important here. So if we then take the partial derivative of G with respect to W1, what do we get? We get, right, we hold everything, all the other variables constant, so this is just a constant. So I get 2 times W1, this is a 2, W2 squared. And the thing, as I said before in the calculus review, I will often drop what this is a function of when we take derivatives. But to make it very explicit, notice that here, this now is actually a function of W1 and W2. Okay, so notice that we've taken the partial derivative with respect to one dimension, but its rate of change is a function of both of the variables now. Okay, so now I'm like, okay, let's go ahead. We need to set this to 0. That's going to tell me that, well, I don't know, because now I need to set W1 and W2. Okay, well, this maybe is not that interesting because it still tells you that W1 is going to have to be 0, I guess. But you can see that in general, you're going to get, okay, so this is the first equation. If you do it for the second one, you're going to get an equation that looks like two times W2 W1 squared. And you need to set that equal to 0. And let me just make this more interesting. Maybe I add a constant 3, just for fun. Okay, that's not that exciting either. Okay, well, I can't think of something great on the spot, but the point of the story is that in general, you can get these like relationships like this. You'll get this system of equations, and you're going to have to rearrange terms to then solve for like W1 first, and then rearrange again to solve for W2, and so on. And since there's two variables, W1 and W2, and you have a system, two equations, like you have a system of two equations, you can actually solve for those variables. And that's going to be kind of the general story for higher dimensions. We're going to get like a system of D equations with D variables, and you need to solve for it. Okay, but in this case, it's kind of obvious. This actually just implies that this has to be equal to 0. And this tells you this should be equal to 0. Okay. But in the assignments and stuff, you'll see other cases. Okay. So that's enough of the optimization review. At this point, basically, that's all the review need to know. And what we're going to get into is how this is now going to map to machine learning and finding, like, searching over functions. And we need to find the minimum function, the function that minimizes this, like, estimated loss, the empirical risk. Is there any questions before we jump into that? Okay. So the obvious thing we're going to try to want to do is somehow reformulate our problem in machine learning into an optimization problem or like a minimization problem over RD. because really it turns out to be the case we're really good at dealing with. So somehow we're going to try to make our domain RD, but we have functions instead of the domain being RD. And we're going to somehow hope that the thing we're going to minimize over, which is that estimated loss, is convex. And notice we have choices over the functions and the loss function. And if we have that, what are we going to do? We're then going to, if this was the estimated loss and it's convex, we're just going to take its derivative with respect to each of the dimensions, which somehow we're going to get this, and set it to 0. So let's figure out how we do that. And this really should be thought of as like, you're massaging your machine learning problem to be such that you can actually optimize it and find the minimum. So like a lot of the choices that are made, right, are such that you can actually solve the problem. So like, remember you saw this whole IID assumption, this independent and identically distributed thing. In practice, it might not always be true about your data, but if you want to think of like how you're going to design your algorithm, how are you going to get an estimate of things, it's good to start with some assumptions, so then you at least know like how you're going to estimate something. It's like, oh, if these were the assumptions, at least I knew I would use this estimate. Now we're going to go into optimization and be like, okay, if I chose this loss function and this function class and so on, then like I know what I would do. I would use these tools. So yeah. So I don't want that to, hopefully it's like, because sometimes it's thought the other way. It's like you're like, oh, we're going to use this machine learning, or in machine learning, now we're going to like do this optimization stuff and pick this law. It's like, well, it kind of goes like kind of the other way. It's like, okay, like if I really would like to maybe use a different loss function, but it's not convex, so maybe I'll just pick this other one that's not quite what I want, but at least I can solve the problem. Okay, enough preamble. Let's solve the problem. So this is going to be like, yeah, like I guess, what do I write? ERM with ERM for regression with linear functions. And really what people call this is like linear regression. Okay, but we're really thinking of it in this viewpoint from machine learning because we're going to change from linear functions quite soon. Okay, so ERM for we're going to talk about regression, right? That means labels are like these things that have some form of order. We're going to consider like real numbers. And our function class is going to be linear functions. That's going to be the idea. So let's write that out. So we have this domain. Okay, let's go back in machine learning world. Forget all about optimization, and we'll jump into it in a few minutes. So we had a domain. Those are our features, RD. Okay. Since we're doing regression, we're just going to assume the labels are the real numbers. Okay. And now we had a function class that ERM needed to choose. The function class was some subset of all functions that map from, I'm just going to write explicitly RD to R, right? D-dimensional features to labels. Okay. We're going to pick this in a second to be linear functions, but that's the setup, right? And we have this data set. The data set is equal to this tuple of n feature label pairs, like x1, y1, up to xn, yn. And here is the function we're trying to minimize in ERM, right? This is what we came to last class. We have L hat of f for a particular predictor is equal to 1 over n, the sample mean of I equal 1 to n of the loss function. We need to choose a loss function of that predictor f at xi compared to yi. Okay. Great. So that is our problem. We have a function. We want to minimize it. We're sort of in good shape. And our goal is we want to find, and I can write this using our new notation now, right? We want to find the arg min f in our function class, the predictor that minimizes what? L hat of f. Okay. And guess what we've been calling this? We've been calling this like f hat. Okay. And yeah. And the reason, okay, there might be some confusion. Like, first of all, like, why do we call this f hat and not f star? We've been calling it w star. And as you like, I don't know, as you're seeing, notation is like sort of important math, because like if you pick right notation, you can kind of get far, because if you define things really nice notation in the simple cases, then when you get to more complicated cases, the notation should tell you what these objects kind of mean or should mean and stuff like this. Okay, so why f hat? Why not f star? And the answer is going to be that we're going to reserve f star for a little bit later in this course for the argmin of L, like the true expected loss, right? So there's a minimizer of the true expected loss, and there's a minimizer of the estimated loss. The thing we really want to find is the minimizer of the true expected loss. We wouldn't want this here, but we don't have that, so we have to use this L hat. So what I really should write is f hat star, but to save, a little bit of ink, I did not put the star, which is commonly done. But that's really what it should be. And maybe I should have done it to be very verbose. But you should really think of this as this is like f hat star. So it's like f star for L hat, and you put this hat thing here. Okay, and in other words, people will say that this is like f hat is like your estimate of f star, which is the true minimizer of the expected loss. Okay, great. So how do we solve this problem? So this is our goal. Apparently I put a box around it and I kind of like it, so I'm going to put it there again. So this is what you want to keep in mind. And we want to somehow map this to what we've just learned in optimization world. And so how are we going to do that? Well, somehow the thing that's really not matching here is the fact that this is a set of functions, right? And before we've been seeing that if this was like RD, you'd be fine. And I guess, I don't know, maybe does anyone have an idea of how to fix it, like what we're going to do here? Okay, well, let's think of an idea here. So like, wouldn't it be great if somehow there was a one-to-one relationship between a function and a number in RD, right? Like, let's imagine that every function is somehow described by a vector in RD. If someone gives you that vector, you're then like, oh, I know what to do. I like somehow take that vector, maybe let's say take the dot product with something else, and then I have my function. So that's going to be the idea. This is called parameterizing your function. And so if you had a function, let's say like f of x, which takes in some vector, right, in RD, and that function was like the x vector, let's say dot producted with a w vector. And notice here that x is like your features, it's in RD. W is going to be called your parameters or your weights. That's not equal. That's also an element of RD. They must both be in RD, and you take their dot product. And in this course, we didn't write this dot. We wrote transpose here. Okay, so that's like one idea. So like, if I change this W, I'm going to get a different function for every value of W. And these functions are called linear functions. You can clearly see it in the case of one dimension. If D was 1, then you would have just x times W, and you would have a line. Right, so in one dimension. So I'm spending a lot of time on this because, to be honest, if you get this idea of that you can parameterize your function class and then optimize over the parameters, which is what we're going to do, then you like made it all the way, basically. Because then all the story is like every function class you really consider in machine learning is just, you want to consider some functions, but you're like, okay, I need to somehow describe them by some giant vector of numbers. And D can be enormous, like billions. Literally, and that will be like that's what people say, like, are all the parameters of my neural network, or stuff like this. And you hear like ChatGPT has like 1 trillion parameters. So D would be like 1 trillion in that case. And then they parameterize that not, they didn't write a linear function, but these values somehow are doing all sorts of other operations. Okay. So let's step back again and just understand, right, this is a line, and let's see some things we're going to do with it. So if you pick a particular W, so this might be something like x times 1, maybe. Maybe I just put 1x. Maybe it's like the thing, and if you had a different line, like you'd have, maybe this is 2 times x. And so on, that's what your W is. And so every number in front of x gives you a new function. And so that's going to be that's what we're going to pick as our function class, called the set of all linear functions. And so let's just write it. The function class is now going to be equal to the set of functions such that the functions map from Rd to R. And you've seen this in your assignments, and now hopefully you're seeing why this was important and stuff. Now we're going to get into defining function classes. You've practiced a little bit of this. And here's the example of the function class that contains all lines. So right, it's the set of all functions such that each function looks of this form. It's just a function of x. And it has this form for some value of w. So you just remove this. That was interesting. You take this, you delete it. You put this here, and this holds for some w. Okay, and clearly we know where x is coming from. This is a domain of x. Okay, beautiful. So the important property now is that every, okay, that's not how you spell it, every f in this function class has a w vector associated with it. And you can do this one-to-one mapping. So I'm not going to write it, but the formal way you say this is, for every f in f, there exists a w in Rd that exactly is equal to that function. And for every w in Rd, if you then take this dot product with x, you then get a function that is in this function class. Okay. So there's one-to-one mapping. That's very wonderful, because now, if we take this problem that we have above, and we write out L hat explicitly, we can then see where w comes in, and then we can change the minimization to w with a slightly different looking L hat function. Okay, and I'm going to keep moving this because we're going to have to update something slightly above, because we'll see. Okay, so we've got this this L hat thing. What is this equal to? This is equal to the argmin in our function class of L hat. What is L hat? 1 over n, sum I equal 1 to n of our loss. We're going to pick the loss in a little bit. But now we've chosen f, right? We can plug in, we can put in f, or we can, okay, so first of all, it's going to be f, right? It's going to be f of xi vector dii like this. Okay, and that's fine. And this is like the way of searching over f's. But you know that f, right, it has this extra structure. So let's do this. So I'm going to write an equivalent version of this minimization. Oh, and I should, okay. Instead of doing argmin, I'm just going to do this as min. So this is the minimum value, because of course, you know, a function is a different object than a vector w. So like the argmin function is not going to be the same as the argmin vector in Rd, but their values are going to be equal, is what you'll see. So far we have that the minimum value of this is obviously equal to the minimum value of this. I've just expanded this thing. And now I'm going to write this slightly different. Okay, so what I'm going to do is I'm going to look inside. I'm going to look inside here. Let me just make some more room. I'm going to look inside here, and I'm going to be like, well, I know f. F has got to be xi transpose times some w. Right? That's what I know it looks like. And I know that since every f has a one-to-one mapping to a w, instead of searching over f, I can search over all functions of this form, which means just search over w vectors that are an element of Rd. Okay, this is a very crucial step, because this is going to happen everywhere in this course. And what's going to happen is f is going to be way more complicated. You're going to write it as like this longer function. It could be a very complicated looking neural network. But once you've plugged in the parameters, you can then just search over parameters. And so we're going to constantly call these things, first of all, like a very important term, which are these called, it's called the parameters or the weights. And yeah, these are the weights of your model. This is your, in machine learning, they call this the model. The predictor is the model. Okay. And yeah, so this is really quite wonderful. And okay, so that's an equality. And so that tells us that what we can do to find f star, right? Or not f star, f hat. It tells us that f hat is going to equal to, right? It's going to equal to somehow like Okay, for a particular x vector, how much time do we got? Oh, this is good. For a particular x vector is going to equal to x vector of, what do I use? Let me just double check. Yes, as you would expect, there's going to be a w hat now. And w hat is going to be the argmin of this expression. Okay, so once you solve the problem above, you found the w. So the argmin is going to give you a w. It's going to give you a parameter. We're going to call that w hat once you solve this minimization problem. You know that w hat, when you take the dot product with x, gives you back the function you wanted. And that's why it's f hat. And that's, yeah, okay, that's that. And like literally, this is what the learner is going to do. So our learner, like, I guess, we'll get back to this, is our learner will take in this data set, it'll output f hat, such that f hat is equal to this, where w hat is the solution to this minimization problem, which we have already kind of seen how we're going to approach solving. And to wrap up a couple things, like we're going to call this object naturally L hat, and we're going to slightly abuse notation. So when L hat took in a function we knew what it meant, when it takes in a parameter vector, like a vector in RD, like W vector, then that means the above thing. And you need to parse this based on inputs, as we've done in other things in this course. And you're like, so we're abusing notation. So this L hat function, when it takes in a parameter vector, means this above quantity, which we're now going to talk about a lot, because now this is the parameterized expected loss, which we can minimize, and so on. And what's going to be left? What's going to be left is to solve this problem. It'll take a little bit of math, but it's not too bad. It's just going to, you take partial derivatives, you have a system of equations, then you just do some linear algebra, which we'll see and solve. And the other thing is, like, before we even do all that, we should probably make sure that this function, right, this is like what we saw before as our g of w vector. And the question is, like, is this convex? Because if we're going to want to use our techniques from before, can we use them? And the answer is going to be yes. And we're going to force it to be convex by our choice of L and the function class. We've chosen the function class as linear functions. It could have been some other parameterized function class, like neural networks or whatever. We chose linear ones. And it turns out if you have linear functions and you pick the loss function as the squared loss, then you do indeed have a convex objective. This is your objective, or your function that you're minimizing, and then everything will work beautifully. Okay, so the answer is yes if L is squared loss. And it's also true if it's the absolute value loss, but there, when you take derivatives, you're not going to be able to take derivatives at that 0 point because of the break, and there you have to use things called subgradients, which really are the same story, but we're not going to do it in the class because it's just extra technical machinery that tells you the exact same thing. Okay, so that's what we're going to finish kind of next class. I think that'll take like 30 minutes or so. And then we'll do like a midterm review. And there's no class on Tuesday. So next, there's like some National Day of Reconciliation or something like this. So then Thursday, I'll do a midterm review on the second half. And then you have, I guess, the midterm on the Tuesday after. Okay, well, thank you and have a good weekend.